Right, so this is just some of the questions that I received during the tutorial session so far, so that I can just consolidate some of the discussion. Don't have to wear my mask for this, I think. Right, so first off, the temperature dependence. So when we have our train of rate constants, Ki triple dash, L sites, AM, and then either C cat or rho bed. Okay, this one, when I consider the intrinsic rate, this has got Arrhenius temperature dependence. So Ki triple dash is K naught triple dash E to the min E over RT. None of these factors carries any temperature dependence with them, right? So they don't affect the fact that all my rate constants, Ki volumetric, Ki area based, Ki dash, the mass based one, all of them carries the Arrhenius temperature dependence, right? However, if I look at Kc, Kc is the one that is so mildly temperature dependent that we can more or less say that it is not really a function of temperature. Or in fact, if I should plot it like in the videos, it's very mild compared to the expected Arrhenius dependency of the true rate constant. So that Robert the Warrior example in Vogler states or shows you why sometimes an engineer needs to be a warrior. Because if you're a warrior and not a warrior in terms of the one with a sword and a gun, but somebody that is concerned about what is really going to happen in your reactor. So if you expected this kind of increase in your rate constant, because you worked with a Ki, you increase the temperature and you expect that, and then in your reactor you only get this because this actually holds back the rate, you are going to be severely disappointed when you complete your design. Right, so this is the one that carries the true Arrhenius dependency. So now another question I got is for a first order reaction. If I consider this sum of resistances, so let's just use for a change the mass-based version of my effective rate constant, and just this is for first order that I can do that, okay? And then I've got 1 over KCAM plus 1 over Ki dash. And if I now take the inverse of that, of course, that will give me that Ki effective. I can see that the Ki effective is equal to the product of KCAM and Ki dash divided by their sum. And if one of the other, so when is a rate constant large and when is it small? So let's just consider the scenario where I want to say external diffusion limits my rate significantly, to such an extent that my surface concentration pretty much goes to zero. So as soon as it hits that surface, so there comes in, hits the surface, gone, hits the surface, gone. It reacts as soon as it hits that surface, right? That means that the KCAM, this one, is really small. In other words, KCAM plus Ki is pretty much just equal to Ki dash. Okay? And then what that implies is that these two terms will fall away and my effective rate constant is only governed by KCAM and its behavior. And vice versa can of course be said when I now have the opposite scenario, when I want to say external diffusion is really fast. If that is really fast, and I should now just rewrite that equation, it means this KCAM is large, and divided by KCAM plus Ki dash, this then becomes pretty much equal to, so let's say this is 1,000 plus 1, okay, which can pretty much be stated that it's then equal to 1,000, and it will cancel out with that term, and then Ki dash governs my rate. And now the question arises, when is it fast? When is KCAM fast enough? And it's always important to note that it depends on the relative size of KI versus KCAM. If I now consider the mass-based versions of these two rate constants. If this one is 0.0001 and this one is 0.1 times 10 to the min 9, this one is very fast. Okay. If this one is equal to 0.1 and this one is equal to 10 times 10 to the power of 3, this one is very fast. Okay, so it's all relative. It depends on the relative size of how fast is my reaction compared to how fast can the stuff be delivered to the catalytically active sites. There's no rule that says a Kc value of that is high. As long as comparably to Ki dash, it is so high that these two will cancel out and that I can actually get my true intrinsic rate that I am interested in. So as far as the temperature dependence are concerned, if I now should once again consider these resistances, right, because it's a sum of the two, this one, and I try to explain it in the video, this one will become faster with temperature, right, because it's got this exponential temperature dependence, whereas this one will remain pretty much the same. And therefore, this initial relationship between KCAM and Ki dash at a T0, let's call it a T0, is going to change. So whether this one is large enough not to matter might change if I increase the temperature, because this one is going to catch up and overtake KCAM much faster than you expect, because this one can't keep up with that increase in temperature. Right, so that is what I wanted to say based on questions I received from the floor. Maybe just on that 6.2, I had some questions on this. That is a real tester of your confidence and whether you understand the concepts here. Let me just get a new page for that 6.2. Right. So if you think about that 6.2, so now you can't use the first order relationships. So you have the two rates that must be equal, and I've got my Ki Ca surface squared. And I based this on volumetric rates. So what you must do now in order to be able to solve this problem is for a CSTR, what is this equal to? Okay, what will change the value of AC? Which parameters will change the value of AC? And remember that this Ki is equal to Ki dash times the catalyst concentration. And Ki dash is equal to Ki double dash times AM times the catalyst concentration. So this is also an AC here. So keep that in mind. What happens in that CSTR, in that 6.2, is that I increase this. So if I increase this, the implication is that the surface concentration is going to go up. But I want this whole relationship to remain constant. So what changes? The Ca bulk must stay the same. So that is a constant. That stays the same. Kc is going to change, AC is going to change, and the surface concentration is going to change. Right, so write it in terms of unknowns, and remember, this equation still applies, so this is an equation that you know, okay? And you know that the volumetric rate that you calculated from run 1, CAS squared, from run 1, that value stays constant. So here you have your second equation. You have two equations. You can solve for two unknowns, but you need to design your problem in order to be able to calculate this. A challenge question for those of you done with all the TATs. Here is a challenge question for TAT 6.2. Challenge question, practice your skills. Do the following. Generate a plot of Ca surface versus RPM in that reactor. So change a range. So in the TUT you were asked for to calculate that CA surface for 2 distinct RPM values as it increases. I want you now to show me, and you can qualitatively say this is CA bulk. CA bulk. There it is. This is 0.5 moles per liter or per cubic meter, can't remember. What's going to happen with CA surface plotted as a function of the RPMs, and also challenge question if you're done with all the TUTs. RPM. What will happen to the catalyst concentration in the reactor as a function of RPM? Test your skills, keep your skills up. Use for loops with the append function so that you don't forget how to use it, that you don't get rusty. So see, okay, so I know people are glaring at me in the class, so it's because they, yeah, I know you must still finish this TUT. So when you're done, this is now I can play. No. So when you have solved the problem, start playing with the problem. Start having some fun and see what happens if you now put that single calculation of yours to calculate it in a loop. Okay, right. It's supposed to be some fun at certain stages of your journey. Right, okay, so any questions from the floor? I'm going to stop sharing my screen. Any questions? Okay, there I've got a comment. Determines the rules. Okay, so not Thiele yet. Alex, we're going to do Thiele next. That was a previous comment, long time ago. Sorry, I missed that. Anybody else with a question that's not in somebody off campus? Want to raise something before I stop the recording? Okay, right.